It's time for a physics class. Okay, so what we're going to be talking about here is what's known as a Gili coil, or it's really just an inductor. It's just a thin copper wire wrapped around in a circle many times to build up an inductor. And what we're going to be doing is we're going to be inducing a current and therefore a potential through this coil, and we're going to be mapping it using vernier and some of the software in our lab to see just what's going on here and what kind of graph will be created if we set something like this up. So let's run over to the lab and see what's going down. So here in the lab here, what we're going to be setting up, we already see here kind of the final, what we're going to get in a second. But what we have is a Gili coil here, and this, it looks very much like this one. This is something that a student made a few years ago. I think this one was like Mason. He did a really good job at building all this. And it's just thin gauge copper wire with an insulator naturally over top of it. And it's just been wrapped around, looks about an inch PVC pipe to make a Gili coil. I'm over here with, I think it's about a 1/2 inch PVC pipe, a little smaller. We'll see why in a second. But it's just wrapped around there and kind of taped to hold it in position. And this will act for us as a solenoid or an inductor. Okay, sometimes they're called Gili coils. What we have here is one hooked up to a test tube. And here we've got two small neodymium magnets. And the reason why we're using neodymium magnets here is these magnets are very strong. But we need to take a few precautions, because if you kind of take a look at these, and we'll bring them to the other cam, if you take a look at them, they're a little chipped in a bunch of spots, and the reason they're chipped there is students accidentally let these fall into each other, and when they fall into each other, they're very brittle, and they'll smash, and they'll chip, and they'll get in people's eyes, and you're like, ah! So one, put on some safety goggles if you're using neodymium magnets, and what I recommend is we've hooked this Gili coil up using a test tube clamp onto a stand holder. This stand holder down here is steel, and these magnets are gonna boom, like they're gonna fall down and accelerate, and they're gonna slam into the steel. So we built ourselves a little crash pad here. It's a little piece of squishy foam in a box, and we're gonna put that under everything, so that when the magnet comes down, it's gonna hit that, and it's not gonna fly everywhere. But what else we're gonna do in this lab is we're gonna start our data collection, and we're just gonna drop the magnet through the tube. And when we do that, we should see a nice data output like we do here. So let's start our data collection, and then drop, and we'll stop it. So let's take a look at what's going on. It looks a little different than what we had before. But if we look at it here, essentially what we see is we've got 0. This is just some noise in the actual voltage sensor that we have. We hooked a voltage sensor up to the top and bottom of the coils. And it's just kind of 0, 0, 0, 0, 0, and then all of a sudden we drop the magnet, and as we do that, we see this change right here and here. So what's going on here? Well, as we drop that magnet and it begins to approach the opening in the coil. So we've got the magnet, and it has begun to approach the opening here. Some B field is going to go through those loops of wire. And as that B field's going through, we've all of a sudden changed the amount of B field, or the flux, that's going through these loops. And we know that a change of flux brings us an EMF, or a voltage. So because that B field is approaching this here, we have a changing B field. That changing B field is going to cause an induced current, and by that an electric potential, an EMF, as we approach that there. Now, in this case, we have a negative, and I think last time when we did this in our first data set, we actually had a positive here. That just has to do with, which direction was your magnet pointing, right? Which direction was your magnet pointing? Which way was north on your magnet? So we get this change right here as the magnet is approaching. Now, technically, we know that as this magnet gets onto the inside here, into the center, we know that we shouldn't be seeing any change. And we've seen problems like that. You're pulling a hoop through a B field going into the out of the page. Whenever you're all fully in the B field, nothing changes there. Well, in a real world scenario, we don't exactly see that, because this B field is falling off with distance away from the magnet as a 1/r² law. And because it's actually just moving so fast through here, we don't really see a full 0 point. that 0 point would happen like, right here whenever you're fully inside of this. And if we had a very, very long Gili coil, we would see something like that. We'd see like, a big dip down here, and then we get onto the inside, we'd see a 0, and then we'd see this big spike up here at the end, which we see. That spike here up at the end is just, now we're not putting B field into the Gili coil or the solenoid, we're taking that B field and moving it out. And it happens very quickly, and we get this spike here. Into the opposite direction because the flux is no longer changing in, but changing out. Now, if we actually take a look at this graph, there are a few very interesting things to note about it. If we take a look at the peaks, the initial peak here and the final peak up here, we'll notice they're different values. The peak down here is negative 0.108, and the peak up here is 1.7. So this one is almost 0.6 larger than the bottom. Why is that? Well, if we think about what we know about EMF, we know that an induced EMF is equal to the negative change in flux divided by some amount of time, negative d flux over dt. So if we're able to change the flux faster, then we're going to get more of an EMF. The 1.7 is going to be larger than the 0.17 is going to be larger than the 0.108. And the reason why that is because as this magnet is falling, the magnet is speeding up. It's accelerating due to gravity towards the ground. So in the beginning, we see some change here, but it's only 0.108. And then at the end, when it's moving faster, we get more flux out of that because, or we get a faster change in flux due to the fact that we've accelerated here. The amount of flux, though, that has changed is actually the same. If you take the EMF that you generate, that voltage, and you multiply it by a time, that is actually going to give you the flux. And that makes sense if you take the equation E equals flux over T, and you just multiply by T, you see that the voltage times the time equals the flux. And what's really cool about that is we'll see that all the flux that we entered into the system is the same amount of flux we get coming out of the system. And that makes sense because the magnet went in and then a magnet came out. Nothing crazy happening there. What this means is that if you take a voltage multiplied by a time, in this case, a voltage times a time is an area. And we know via calculus that if you wanted to find an area of a weird shape like this, we can integrate it. In this case, Vernier will do it for us, so we can go down here and we can view the integral. What we'll actually see is that our area here is 2.871 times 10 to the negative 4. So it's like 0.0002871, which that might as well be 0. And that means that all the flux you got in is all the flux you got out. This area underneath the curve here, or rather, this area underneath the x-axis is the same amount of area as above the x-axis. It's just that this one is shorter and wider. This one is tall and skinny. Okay, so that's a really cool way to look at what's going on here with fluxes, with something like a Gili coil or an inductor where you're dropping a magnet through it and we see these potentials generated and what the actual graph from that means. So pretty cool thing going on there, just depending on what you got. So with that, you should have a pretty good understanding of what's going on with our inductors, how these B fields are moving into things, and hopefully that was a nice little pseudo virtual lab for you to take a look at. But until next time, adios, and y'all take it easy.